Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online course on techniques of materials characterization. We are in module 11 and we are continuing with X-ray diffraction. Basically, we are continuing with intensity of diffracted beam. In the last class, we have talked about the structure factor calculation. We have derived an expression of structure factor, and in this class, we will be continuing with calculation of structure factor for various crystal systems. We will start with a simple crystal structure. Then we will go for a base centered crystal structure, body centered crystal structure and face centered crystal structure, and we will try to show the differences, similarities of this the various structure factor of this various crystal structure. So, before we begin, basically let me again give you a quick recap and derive some useful relations about structure factor. So, if you remember, we have derived the structure factor in this way. Basically, we said the structure factor is the way it is. Okay, I think there is a little problem here, so check it out. And the way we can define the structure factor is basically this, where for n number of atoms, we take a summation of these waves that is scattered by each of them, that is diffracted coming out of each of these atoms, and finally we are saying that this one, if we express this again in terms of the particular phase and amplitude. So, amplitude is basically represented by the atomic scattering factor, whereas phase is represented, we have already derived, it is represented by this relation 2 pi HU plus KV plus LW, basically through the fractional coordinates of this second atom here. So, some useful relations that will help us to derive the specific structure factor relations for various different type of crystal structures. So, we will be writing it here. Number 1 first, and these are basically simple mathematics. This is nothing special. This is simple complex number mathematics and simple equations for power series expression. So, if we have something like this, e raised to the power pi I equals e raised to the power 3 pi I equals s raised to the power 5 pi I. Ultimately, this all boils down to minus 1. Okay. Then the second one, that means if pi is an integer multiple of this entire there is an integer I and then there is an integer multiple of this which is even here, which is odd. Now, we will see if that is an even. So, if we have an even multiple of I, then what will happen? This like e 2 pi I, e 4 pi I, and then we have e 6 pi I, all of this will be 1. So, the general rule that we can write down is basically e n pi I will be minus 1 raised to the power n, where n is any integer. Okay, fine. And also we can write, this is one, and also another one we can write e equals n pi I equals minus n pi I. This is also is valid, where again n is any integer. So, what this one means basically, this one is like e n pi I equals minus 1 raised to the power n. Let us say n is 135, all of this, that means minus 1 raised to the power 135. Okay. In that case, it will be minus 1. So, if n is an odd number, then it will come, the value will be minus 1. If n is an even number, the ultimate value of n pi I will be even number. Okay. So, or it will be 1, and if it is odd number, odd multiple of pi, then this will be an odd, then this will be minus 1. And also we can convert E n pi I and E n minus pi I is the same. That means E being any integer. Okay. So, E pi I equals E minus pi I. So, that is another very important relationship, and the final relationship that we can write, which will be useful for us, is basically E into I x, E I x plus E minus I x equals 2 cos x. This is basically the way E is explained. If you remember, E pi x is equal to what we said, E I x is basically expressed as cos x plus I sin x. This is how the complex numbers are basically expressed. So, if you add them up, then you will be getting the same. So, these are the very useful relationship that we will be using while deriving the structure factor for various atoms, various crystal systems. Okay. So, one thing before going there, one final thing about structure factor that we must understand is that the structure factor basically describes the waves scattered from the unit cell by adding together waves, and waves which are coming from different atoms, just like here we are adding up one wave coming out from this set of plane H00 planes, and the waves coming out from another set of planes B, okay, which are having a differing in phase and may differ, may or may not differ in amplitude, that does not mean. But the point here, important point here, is that there is no phase difference between the rays coming out from A and C. These two planes, this H00 planes, between the H00 planes. For example, if I take 100 planes and 200 planes, there is no difference between their phases. That is what. And they may have a phase difference between this set of planes and this set of planes, but individually between them there is no difference in place. That is the assumption of calculating the structure factor. Basically, this is not very true, because we know that as we are in X-ray diffraction after a certain maybe in the next module we will discuss, or during discussion in electron diffraction, we have seen that the Bragg's condition is also satisfied for this theta b, the angle for which the Bragg's condition is satisfied. This has a range. This is not an exact angle. This is, there is a finite range of, because of which we have seen that Ewald sphere touches, when it becomes a cylinder, the points become cylinder and so on. In case of electron diffraction, similar things we will be seeing in case of an X-ray diffraction, where it leads to a broadening of the peak. But basically, this diffraction conditions are satisfied for a range of angle, not only at a single Bragg's point. So, that is why there the waves that is generated between this atomic plane and another atomic plane, this can be for an angle of theta plus theta b. A little bit deviation can be there, but when we calculate the structure factor, we safely can ignore this, and we can just imagine that the structure factor represents basically the waves coming out from one set of plane which does not have any phase difference between themselves, and another set of plane which again does not have. So, this set of plane and this set of plane, they will not be having any phase difference between them. So, only between themselves they will be having a phase difference. So, this is an important point to consider, and we should not get confused later when we discuss about this phase peak broadening and so on. Okay. Now, let us forget all of this and let us start doing some simple, very simple and fun things, calculation of structure factor for various type of crystal system. So, this is a simple crystal structure. So, simple crystal structures, how do we define a simple crystal structure? Basically, a simple crystal structure has, if we consider something like a orthogonal crystal system, that means this angles, we imagine that all of these angles are 90 degrees. So, this is a simple, this is also, so we could imagine that these angles are not 90 degree, but that will be just little bit more complex to understand. So, we imagine that this is a simple structure and all these angles are like 90 degree to each other, and a simple structure is defined with atoms in all different corners. So, this is not a closed pack structure. So, atoms in all different corners, and these atoms are basically shared with 8 other such unit cells. So, we have 8 atoms in 8 corners, and all of these atoms are shared with 8 other unit cells. So, their individual contribution is 1 by 8, and finally, that means the effective number of atoms within this simple unit cell is 1. Fine. Now, the fractional coordinates, that is UVW, we can represent this for this one. If we represent this, let us say 0, 0, 0, that is this origin, if we think that this is the origin, right. So, another atom will be here, correct. So, this another atom anywhere, this one, this one, this one, this one, anyone. So, the another atom should have its fractional coordinates at 1, 1, 1, okay. Point is, this 0, 0, 0 and 1, 1, 1 basically will be, can be interchanged. I can just simply shift the origin here, and then this atom which I was like imagining that this is 1, 1, 1 now becomes 0, 0, 0. So, that means effectively this UVW here is, we can write for all kinds of atoms in this structure, the UVW, the fractional coordinates for them will be 0, 0, 0. One single atom at fractional coordinates of 0, 0, 0. That is what, nothing else. So, or other way around, we can say that this is, let us say 1, 0, 0 plane is this, there is nothing in between, the another plane is another type of 1, 0, 0. So, if we draw something analogy with this, what we are doing here, we have just this one set of plane present here. There is no other atom, no other plane present in the entire calculation, nothing comes in between. So, the structure factor of this simple structure is also comes if we write this F equals, and we imagine that one single atom, this has one single atom, there is no difference between the atoms. If these atoms are of two different types, it is not a simple structure, crystal structure, it will become some other type of crystal structure. So, we imagine all of these atoms are of the same type, and then their amplitude can simply be represented by their atomic scattering factor, and then we can write for them the expression, because 2 pi I, you know, this HU plus KV plus LW, and since UVW equals 0, what we can write, F 2 pi I H into 0 plus K into 0 plus L into 0 finally comes down to be F. That means, the intensity, which is basically nothing but square of the modulus of structure factor, simply will come down to F square. Fine. So, what does this mean? This means that for every kind of HKL, any diffraction condition for any kind of plane, be it 100, be it 110, be it 111, any kind of plane, we will be getting an intensity, some amount of intensity. None of these planes or none of these diffracted beams will be absent. All of them should be present in the X-ray diffraction pattern, because for all of them, because what is it means is that structure factor, basically the expression of structure factor, it does not contain any particular expression from the atomic positions or the plane itself. So, that means for all possible planes, all possible HKL, there will be certain amount of intensity which is expressed by this F square term. So, let us see then this X-ray diffraction pattern of a simple cubic structure. So, this one is given from a perovskite structure, simple perovskite, simple cubic perovskite unit cell, strontium, cerium, titanate, and here if you see, you will see that there are all kinds of planes are present. 100 is present, 110 is present, 111 is present, 200, 211, 210. So, there is no restriction on any kind of diffraction plane, any kind of diffracted beam. All possible diffracted beams are present here, and their intensity is simply varying as F square. Now, you can see there are huge difference in intensity between this peak and this peak and this peak. This is coming for other factors which we will discuss later, this kind of intensity difference. But from structure factor calculations, that is, since we know that F equals F, this basically the intensity will be simply a square of the atomic scattering factor. The way atomic scattering factor varies, and atomic scattering factor, of course, one more thing you should remember here, the atomic scattering factor for 100 planes and 110 plane is not the same, right, because sin theta by lambda for 100 plane sin theta by lambda, lambda being constant. Let us imagine the lambda constant, but still sin theta is changing. So, even if lambda is constant, sin theta for this 100 plane and this one 110 plane will be different. Sin theta is increasing here, as we know from this relationship. If you remember this relationship between the atomic scattering factor and sin theta by lambda in pi, it varies like this. So, if we are moving in this direction, the atomic scattering factor is also decreasing. So, that means ideally from 100 it should continuously decrease. If there is no other effect, that is why I said that there are many other effects. If there is no other effect, then the intensity of these peaks will simply decrease as per atomic scattering factor, but there are many other factors which is controlling this intensity of these diffracted beams. So, if there are no other factors, no other things are controlling the intensity of this, so then what we should get, the 100 peak should be the maximum intensity, then the next intensity should be 110, then the next intensity should be 11. So, this will be 100, this is 110, this is 111. So, this way it should vary as per this, because here atomic scattering factor, if we look, this is possibly 100, this is 110 and this is 111. This is for sin theta by lambda from there. So, intensity also should vary in that same way, but it is not happening even for a simple cubic, it is not happening simply because the diffracted beam intensity depends on many other factors, some of them which we will be discussing in the next few classes. Okay. So, this is for simple cubic structure, where we understand that all the diffracted beam from all kinds of atomic planes are possible. Now, let us calculate for another kind of crystal structure, base centered. So, what is a base centered crystal structure? If you again let us imagine that same thing, that we are basically base centered crystal structure is most prominent in base centered orthorhombic crystal structure. That is why we have written that this is, we have imagined a special case that this is base centered orthorhombic crystal structure, where A, B, C, A not equal to B, not equal to C, but alpha, beta, gamma equals 90 degree. Okay. So, this contains two sets of atoms, as we can understand. One set of atom is basically forming the corners, again 8 corners, and they are giving 1/8 contribution. Okay. Plus I have two different atoms, one here and one here. So, two different atoms, and they are giving, they are shared, these two are shared with another unit cell. So, this is shared with another unit cell in below this is shared with the another unit cell which is above this. Okay. So, their contribution will be half. Altogether I will be having 1 plus 1. So, one atom that is coming out of this cornered cells and one atom effectively that is coming out of this base centered position. So, how do I define these two atomic positions? Okay. So, of course, the one which is in the corner we have just seen from simple cubic. If anything is in the corner, we can simply write its fractional coordinate. This is basically UVW as 0, 0, 0. What about this? For this UVW will be something like what we can write half 0. Okay. So, that will be the fractional coordinate, you can check it here. So, if you move half distance, if you move half distance in the x direction, then you move half distance in the y direction, half means half of A. So, if you move half of A here, half of B here in this direction, and no movement is needed in the C direction, you will be reaching to this base centered atom. So, that is why I said that this is the position for base centered atom, and this is called base centering translation, base centering translation. Okay. So, if you start with the 0, 0, 0 corner atom and then you apply this base centering translation on this atom, you will be reaching to this base centering position. That is what. Okay. So, simply again we will be doing the same thing, we will use the same expression for F equals, now we imagine that again they are of same type, we do not go into complexity, we just imagine that all of them are the same type of atoms. So, we simply have this multiplication with the atomic scattering factor, and for this atom, okay, for this base atom what we have 2 pi I into H into 0 plus K into 0 plus L into 0, okay, plus we have this base centering atom. For that we can take 2 pi I H into half plus K into half plus L into 0, okay. Altogether what we will get is F into 1 plus E pi I into H plus K, right. If you do this, if you solve this one, this is ultimately the expression that we receive for a base center, the structure factor for a base centered crystal structure, right. Now what happens here? We have already done this useful relationships. We know that what it should take, this value for even. So if we now imagine that H plus K, two different conditions can happen. Either H plus K can be even or H plus K can be odd, and depending on that this entire expression will change. So if H plus K is, let us say we imagine that H plus K is even, then F, what will happen to F? This will happen, H plus K is even, that H this, then F will be. So we know that if for even this comes out to be E, we know this, right, E n pi I equals minus 1 raised to the power n. So that means if this is even, then this is plus, this is minus I, right. Yeah, this is plus, sorry, this is 1. If n is an even number, then this is 1. So that if this is A, this one is an even number, this H plus K is even number, then we get F equals 1 plus 1, that means it is 2F, okay, and intensity in that case I will be equals to again F square, that will be 4F square. So this is for H plus K even, right. Now how we can have H plus K even, and if what also we will see that if what will happen if H plus K equals odd, then again what we will have F equals F into 1 minus 1 from the same relationship, 1 minus 1 equals 0, right. So I will not get any intensity from this. Now we have to solve it a little more. How we can make a H plus K? H plus K equals even. So this is possible when we have H and K unmixed, that means unmixed. What does it mean? Unmixed means either H and K both odd or both even, okay. So both, that means both odd or both even, right. If this is true, then this will be H plus K will be even, that means either we can have both odd or both even. If they are both odd, let us say both odd means they are 1 and 1, it will be 2 equals 1 and 1 plus 1 equals 2, or both odd, and odd means, and in this calculation we will be imagining 0 also as even number. We will start the even number not from 2 but from 0. So let us say H and K, one is 0 and one is 2. Again if we add them up, that will be 2, and that means that will be an even number. So this means finally the relationship comes down to be H K either both even, they should be unmixed, either both even or both odd. In that case I will be getting a reflection, I will be getting the diffraction, and this will be their intensity. And on the other way, if H plus K, the way they can go for odd is basically if they are mixed, that means one of them is even and one of them is odd. If they are mixed, then their H plus K is odd and I will be getting no intensity at all. That means mixed means one is, let us say 0, 1, and or otherwise we can imagine that one is 0, one is 1, or 1 is 1, 1 is 2, so on and so forth. So, this kind of a combinations will give me no intensity at all, even though the Bragg's condition is satisfied, that then also we will not get any intensity from those particular atomic planes. Now, one thing you must understand, let us see this crystal structure for a base centered orthorhombic crystal, and you can see that we are getting intensity, first intensity we are getting from 0 to 0. That means here H equals 0 and K is 2. So, we are getting an intensity from there. Next one we are getting where H equals 1, K equals 1, right. The third one we are getting 2, 0, 0, H equals 2, K equals 0. So, all of these cases this is unmixed, that means both of them either they are both odd or they are both even, either they are both even or they are both odd, but we are not getting from any of the conditions, we are not getting where they are unmixed. Okay. So, they are, if they are mixed, we are not getting any kind of diffraction from those kind of structure. But one thing you must notice here is that only important points are H and K, not the L. So, L is can be independent in this case. The L value of L is not at all important in this for calculating for the base centered condition. So, we can have reflections from any combination of H and K, and we do not need to bother about L at all. For example, one second, we can, yeah. So, L is not at all important in calculating the intensity in this case. For example, if we have something like 111, if we have something like 112, if we have something like 113, all of them will have the same intensity because H and K are the same. So, all of them will have an intensity of 4f square. The L value does not make any difference because their H and K value is important here. Similarly, we can imagine that something like 0 to 1 or 0 to 2 or 0 to 3, all of these planes will have diffraction and will with the same kind of intensity as per the structure factor. Of course, as I said, the structure factor is not the only factor which sort of depends or which controls the intensity, final intensity. There are other factors, but as per the structure factor calculation, all of these planes will have the same intensity for the diffracted beam. It does not matter what L value, the final one, what is the L value, it does not matter at all. Only the first two H and K matters for this kind of calculation. So, okay. So, now if we calculate, if you compare the X-ray diffraction pattern from a base centered and a simple orthorhombic, it will become much more clearer. So, base centered one, the base centered one is given here, and I think the simple orthorhombic is this one. The bottom one is simple orthorhombic for iron sulfide and iron selenide. So, iron sulfide is a orthorhombic, base centered orthorhombic crystal structure, whereas iron selenide is a simple orthorhombic crystal structure. So, you can see for iron sulfide, which is a base centered one, this you are getting diffraction from 111 peak, you are getting from 200 planes, you are getting it from 210 plane. Okay, this is a little odd because it should not get 200 planes, but anyway, there must be some other factors. But iron selenide, which is basically the normal orthorhombic, simple orthorhombic, you are getting from 110 planes, which is not allowed for Fe, Se. So, 110 planes, no, this is a little problem, I think. Okay, fine. So, we will stop, I think, here, but we will be continuing with this structure factor calculation for body centered crystal structure and all other different other crystal structures. We will be continuing with this in the next class. Thank you.